Imagine that tomorrow, scientists confirm it, an intelligent civilization exists just 1,000 light years away, alive and thinking right now. The headlines would scream that we are not alone, and the celebrations would be real. But here is the part almost no one mentions. 1,000 light years means any signal we send today would not arrive until the year 3026, and their reply would not reach us until the year 4026. By then, every person alive tonight will have been dead for 2,000 years. The civilization that sent the first message might be gone. The one that reads the answer might be gone too. The nearest minds in the galaxy could be real, awake, and wondering about us, and still be too far away to ever matter to us or us to them. Settle in and make yourself comfortable. Subscribe to Sundown Science if you haven't yet, because by the end of this, you will understand why even our nearest neighbors in the galaxy may stay forever out of reach. Now, let's slowly slip into this. Part 1. The word that quietly lies. There is a single word that has quietly sabotaged almost every serious conversation our species has ever had about life beyond Earth. The word is closest. It slips into a sentence without resistance, soft and reasonable, asking nothing of us. The closest star, the closest habitable planet, the closest civilization. Each time we say it, something in the mind performs a silent translation that we never authorized and never notice. Closest becomes reachable. Closest becomes relevant. Closest becomes the one we will eventually meet or contact, or at the very least detect. The assumption feels so natural that almost no one stops to examine it. And tonight, slowly and carefully, we are going to examine it, because it is one of the most beautiful mistakes the human mind reliably makes. The reason the mistake feels like truth is not that we are foolish. The reason is that we are old, far older as a kind of animal than as a kind of thinker. Human beings spent hundreds of thousands of years in places where nearness was the single most important fact in every decision that mattered. The closest water decided whether a family lived through the dry season. The closest predator decided whether you ran or stood your ground. The closest shelter decided whether you survived the night the temperature fell. Across that long apprenticeship, our ancestors grew brains that treated distance as a measure of importance. Things that were near could feed you or kill you. Things that were far could be safely ignored, because by the time they arrived, if they ever did, you would be ready or you would be gone. This way of seeing the world was not a flaw, it was a triumph. It worked on the open grassland, and it worked in the first walled cities, and it still works tonight when you choose the grocery store 3 minutes away over the one across town. The instinct is so reliable that we forget it is an instinct at all. We experience it as simple common sense, the obvious truth that what is close to us is what concerns us. The trouble is that this flawless tool was built for a world that ends a few miles past the horizon. It was never tested against distances, where the unit of measurement is the time light takes to travel, and when we finally carried it out into that world, it broke in a way we have still not fully admitted to ourselves. Consider how astronomers use the word. When they speak of the nearest star system to our own, they mean Alpha Centauri, a family of 3 suns sitting roughly 4.24 light-years from where you are sitting now. Within that family, the closest single star is Proxima Centauri, a dim red ember orbiting the brighter pair at a wide remove. 4.24. Say it aloud and notice what your mind does with it. It is a small number. It has a single digit before the decimal point. Your brain, trained on a lifetime of small numbers, files it gently alongside the others it already knows. 4 miles to work, 4 hours to the coast, 4 days until the weekend. The number sounds like something a human life can hold. It is not something a human life can hold. 4 light-years is a distance so large that ordinary language buckles under the honest weight of it. 1 light-year is about 5.88 trillion miles. Multiply that figure by 4.24 and you arrive at roughly 25 trillion miles to the nearest star that is not our own sun. The number has not gotten bigger in a way you can feel, because the human mind does not feel the difference between 1 trillion and 25 trillion. Both simply register as a great many. That failure of feeling is the entire problem in miniature. The distance is real and the comprehension is not, and into that gap between the real and the felt, the word closest pours all of its false comfort. So let us be precise about what we are claiming, because everything that follows depends on it. We are not going to argue tonight that we are alone. We are not going to argue that no one is out there, or that the universe is sterile, or that intelligence is some freak accident that happened only once. The argument is stranger, and, in some ways, lonelier than that. The argument is that the existence of our neighbours and the possibility of reaching them are two completely separate questions, and that we have spent decades quietly mistaking one for the other. The galaxy may be alive with minds. The nearest of those minds may be real and awake and wondering about the same silence we wonder about. And it may still be too far away to ever matter to us, or us to them, in any sense the word matter has ever carried. It is worth noticing how invisible this translation is, because that is what makes it dangerous. You do not consciously decide that closest means reachable. The decision is made for you, below the level of thought, by machinery older than language. A child does not have to be taught that the nearby fire is the one that can burn her, or that the voice across the room belongs to someone who can answer if she calls. Nearness and response are fused together in us so early and so completely that we never experience them as two separate things. And so when an astronomer says a world is the nearest of its kind, the mind does not hear a fact about geometry. It hears a quiet promise that this is the one we could touch, the one that could touch us back. The promise was never made. We supply it ourselves, every time, and then forget that we were the ones who added it. Hold on to a single sentence, because we are going to return to it many times before the night is over, and each time it will weigh a little more than it did before. Closest does not mean reachable. On Earth, it always did. Closest meant the friend you could call, the help you could summon, the door you could walk through. We borrowed that word, with all of its built-in promise of access, and we draped it over a cosmos that honours none of that promise. The cosmos kept the word and threw away the meaning, and the first crack in our comfortable picture of the universe opens exactly here, in the moment we realise that the most reassuring word in the whole conversation has been emptied out from the inside and that we never heard it happen. Part 2. Even the nearest star is an abyss. To understand how completely the word closest fails us, we have to stop talking about the nearest civilization for a moment and talk about something far simpler and far closer. We have to talk about the nearest star, because if we cannot honestly cross the distance to a single burning ball of hydrogen, we have no business imagining a casual conversation with whoever might be orbiting one. Proxima Centauri is the easiest interstellar target the universe offers us, the lowest possible bar, and it will be instructive to watch ourselves fail to clear it. The farthest any human-made object has ever travelled from Earth is the spacecraft Voyager 1, launched in 1977. It has been flying outward, without rest, for nearly 50 years. It moves at roughly 38,000 miles per hour, which is not a modest speed for the listener to wave away. At that velocity, you could cross the entire United States, coast to coast, in under 5 minutes. Nothing you have ever ridden in comes anywhere close to it, and nothing you ever will ride in likely will either. After almost half a century of that relentless pace, Voyager 1 has covered around 15 billion miles, which is a genuinely staggering achievement by every standard that human engineering has ever set for itself. Now set that achievement against the distance we are trying to cross. 15 billion miles is less than 0.1% of the way to Proxima Centauri. Read that again slowly. The most far-flung object our entire civilization has ever built, after 50 years of continuous flight at a speed that would carry it across a continent in the time it takes to boil an egg, has not completed even one part in 1,000 of the journey to the nearest star. If Voyager 1 were aimed directly at Proxima, which it is not, it would arrive in roughly 75,000 years. Let me give that number a body you can stand next to, because 75,000 years is exactly the kind of figure the mind waves through without inspecting. The entire span of recorded human civilization, every empire that ever rose and fell, every language ever written down, every war, every cathedral, every symphony, every equation, fits inside the last 5,000 years or so. Voyager's crawl to the nearest star would last about 15 of those spans, laid end to end, 15 complete cycles of everything we have ever called history. The spacecraft would finally reach that star system, having outlived not just every person now alive, but the whole concept of the present, 15 times over. Close your eyes for a moment and ride with it, because the numbers want to become a place. You are strapped to Voyager 1 on the day it leaves. Behind you, Earth shrinks from a world to a marble to a pale blue point, and then to nothing your eye can hold. The sun follows it down, dimming year after year, until it is only the brightest star in a sky of stars, and then merely one of the brighter ones. You are moving fast enough to cross a country in minutes, and you can feel in your bones that you are moving. The decades pass. A human lifetime passes outside the window, and you have barely begun. You look ahead toward Proxima, expecting it to grow, to swell, to become a destination. It does not move. It hangs exactly where it hung on the day you left, a fixed red point that 50 years of impossible speed have not nudged a hair's width nearer to your reach. The speed is real. The motion is real. And against this distance, both of them are nothing at all. That is the first taste of what space does to human effort. It accepts everything we have and gives back no visible progress. And here is the part that should reorder your sense of the whole conversation. Proxima Centauri is not the nearest civilization. Proxima Centauri is not even a candidate for life as we know it in any confirmed way. It is simply the nearest furnace, the closest place where hydrogen is fusing into helium that is not our own star. We have just watched our finest spacecraft fail by a factor of more than 1,000 to reach the easiest possible target, a target that thinks nothing, builds nothing, broadcasts nothing, and waits for no one. Everything we are about to say about reaching another mind has to be built on top of this failure, not instead of it. This matters because the conversation about alien life almost always begins one step too far down the road. It begins with the civilization, with the signal, with the handshake across the void, and it quietly skips the part where we admit we cannot yet cross to the nearest star with a robot the size of a small car. When someone says a habitable world has been found in our cosmic neighborhood, the mind hears a place we could go. But we have just seen what going means at these scales. Going means 75,000 years to the absolute nearest star, using the fastest thing we have ever launched, to arrive at a system with no promise of anything alive in it. The word neighborhood is doing the same quiet work that the word closest did a moment ago. It is borrowing the warmth of human scale and spending it on distances that have no warmth to give. So we begin our climb already humbled, and that is the right place to begin. We have not yet added the speed of light's cruelty, or the problem of sharing a moment in time, or the difficulty of being heard across the noise of the galaxy. We have only measured the gap to the nearest star with the best ruler we own, and found that the ruler runs out almost immediately. Keep Voyager in your mind as we go, that small, brilliant, doomed traveller making genuine progress that amounts to nothing, because it is the honest image of every interstellar hope we are about to examine. The distance is not waiting to be beaten by a better engine. The distance is the kind of thing that swallows engines whole and asks for more. Part 3. The illusion that regenerates with every headline. The illusion of nearness does not stay safely in the abstract. It renews itself again and again every time the sky hands us a new discovery, and it feeds on headlines the way a fire feeds on dry grass. To watch the pattern work, we only have to look at the last year or two of genuine, careful, exciting science, and notice how each finding gets translated into a promise that the science never made. In November of 2025, a team at the University of California, Irvine, announced the detection of a habitable zone super-Earth candidate orbiting a star called GJ 251, sitting roughly 18 light-years from Earth. The planet falls in the orbital band where liquid water could, in principle, exist on a rocky surface, and the researchers described it as a promising target for direct imaging by future telescopes. The coverage arrived warm and immediate, 18 light-years. The number sounded close enough to photograph, close enough to study, close enough to lie awake thinking about. Then, in early 2026, a study accepted for publication in Astronomy and Astrophysics confirmed something even more tantalizing. The nearby red dwarf GJ 887, one of the brightest stars of its kind in our sky, was shown to host at least 4 planets, and one of them, GJ 887d, sits squarely in the habitable zone, just 10.7 light-years away. That made it the closest habitable zone world we know of, after Proxima Centauri b itself. The headlines practically wrote themselves. A potentially habitable world, right next door. Around the same time, the European Southern Observatory's Near-Infrared Planet Hunter confirmed the existence of Proxima Centauri d, sharpening our picture of the very nearest planetary system to include at least 2 confirmed worlds, with Proxima b sitting in the habitable zone at 4.24 light-years. Every one of these discoveries is real. The planets exist. The measurements are precise and hard-won, the product of instruments and patience that should make any thinking person proud of what our species can do with a telescope. And every one of them landed in public as though the most important thing about a planet were how near it happens to be to us. In a narrow and honest sense, nearness truly is valuable. Nearby planets are easier to observe, easier to weigh, easier to study with the instruments we actually possess. Proximity buys you precision. But proximity is not the same thing as accessibility, and the language we use to report these worlds erases that distinction so smoothly that we never feel it go, right next door. In our cosmic backyard, close enough to study. Each of these phrases quietly borrows the emotional heat of human-scale nearness. The backyard you can walk into, the door down the hall, and pause it over distances that remain, for any purpose beyond looking, effectively without end. GJ 887d, at 10.7 light-years, is about 63 trillion miles away. At the speed of the fastest spacecraft we have ever built, the crossing would take on the order of 200,000 years. The planet is close enough to examine through a powerful telescope. It is not close enough to visit, to contact, or to trade a single sentence with on any timescale a civilization could survive. This pattern is not new, and that is what should give us pause. Every generation projects reachability onto the nearest promising candidate, and then watches reality strip the projection away. In the late 19th century, the astronomer Percival Lowell convinced himself, and much of the public, that Mars was laced with canals, enormous engineering works built by an intelligent species struggling to move water across a drying world. Mars was close, Mars was visible. It had polar caps and changing seasons, and the story of a Martian civilization survived for decades, sustained by exactly the instinct we have been describing, until sharper observations revealed the canals to be tricks of the straining eye and the surface to be a cold, irradiated desert. In the early 20th century, Venus took its turn as the nearby world of our dreams, imagined as a steaming jungle hidden beneath its clouds, populated in story after story with swamps and oceans. Then the Mariner probes of the 1960s arrived and found surface temperatures above 450 degrees and an atmosphere of crushing carbon dioxide. Every nearby world that looked like a haven turned out, on closer acquaintance, to be hostile, sterile, or simply nothing like the home our imaginations had furnished. The same cycle is beginning again, now with worlds light years away instead of planets next door, and the engine driving it is a single, slippery word. That word is habitable. It sounds like an invitation. It is not. Habitable does not mean inhabited. It does not even mean capable of supporting life. It means only that a planet orbits its star at a distance where liquid water could, given the right atmosphere, exist on the surface. The zone is defined by temperature and almost nothing else. Whether the planet actually holds an atmosphere, whether it has a magnetic field, whether it is geologically alive or bombarded with radiation, whether it has any water at all, these are unknowns for every single one of these worlds. Habitable zone is a statement about orbital geometry. It is a fact about where a planet sits, not about what is happening there. But the word sounds like a promise, and our pattern-hungry minds accept the promise without reading the contract. So we should be clear and a little merciful with ourselves about what is actually happening when these announcements arrive. The science is doing exactly what good science does. It finds a world, measures its orbit, estimates its temperature, and reports the result with appropriate caution. The failure is not in the finding. The failure is in the translation, the silent step where nearby habitable zone planet detected becomes, in the listener's mind, place we could go or place where someone might be waiting. And the distance between those two readings is the same distance we have been circling all night, the gap between what is real and what evolution wired us to feel. Each new discovery is offered as a data point and received as a destination. We keep mistaking a measurement for an address, and every time we do, the old reflex stirs again, whispering that this one, finally, is close enough to reach, while the cosmos, patient and indifferent, keeps the word and quietly discards the meaning. Part 4. A star is not a civilization. There is a quiet substitution running underneath everything we have said so far, and it is time to drag it into the light. When we talk about the nearest civilization, we slide, without noticing, into talking about the nearest star, as though the two were the same thing. They are not the same thing, and the difference between them is enormous. A star is only a furnace. It does not think, it does not build, it does not broadcast. To go from the nearest star to the nearest civilization, we have to pass through a long chain of conditions, and at every link, the number of candidates falls. Picture the chain honestly. We need a star, and then we need that star to host a planet, and then we need that planet to sit in the orbital zone where temperatures permit liquid water, and then we need it to have held on to an atmosphere, and then we need that world to have developed complex chemistry, and then biology, and then, from biology, intelligence, and then, from intelligence, technology capable of crossing space with a signal. And then, after all of that, we need one more thing that is easy to forget and impossible to skip. We need that civilization to be doing all of this right now, in the same narrow window of cosmic time in which we happen to be listening. Each link in that chain cuts the field of survivors. By the end, the number that remains is not the 400 billion stars of the galaxy. It is something far smaller, and we do not know how much smaller, because the universe has so far declined to tell us. Here is the one number we can state with confidence. The count of stars currently known to host a detectable technological civilization after every search in the history of science is 0, with a single exception, and that exception is us. This does not mean no one else exists. It means only that whatever the true number of civilizations may be, it is small enough relative to the staggering volume of the galaxy that the nearest one could be extraordinarily far away, far enough that the word nearest loses the last of its comfort. The tool we use to think about this was built in 1961 by the astronomer Frank Drake, and it is less an equation than a way of organizing our ignorance. The Drake equation estimates the number of communicating civilizations in our galaxy by chaining together a series of fractions. It asks how fast stars form, how many have planets, how many of those planets develop life, how much of that life becomes intelligent, how much of that intelligence builds technology we could detect, and, crucially, how long such a civilization lasts before it falls silent. The honest truth about the Drake equation is that we have firm values for almost none of its terms, which is why the estimates it produces range across an absurd span from millions of civilizations down to the possibility that we are the only one. But even the cheerful end of that range carries a consequence most people never sit with, a spatial consequence that turns optimism itself into a kind of loneliness. Suppose we take the bright, generous case and imagine that 1 million civilizations exist in the Milky Way right now. A million sounds like a crowd. It sounds like a galaxy humming with company. But the galaxy is a particular size, and we can ask what 1 million civilizations actually means for the distance between them. The disk of the Milky Way is roughly 100,000 light-years across and about 2,000 light-years thick. Scatter 1 million civilizations evenly through that enormous volume, and the average separation between neighbors comes out to somewhere around 200 to 300 light-years. That still sounds almost manageable until you remember what a light-year is and what a round trip across one of these gaps would demand. 200 to 300 light-years of separation means a single exchange, a message and its reply, takes 400 to 600 years to complete. Send a greeting today in the most crowded galaxy anyone seriously proposes, and the earliest possible answer arrives centuries from now, long after everyone who composed the question is gone. Now let the optimism cool a little toward numbers many researchers consider more reasonable. Suppose there are 10,000 civilizations in the galaxy at this moment. The average distance between neighbors climbs to roughly 1,000 light-years, and a round-trip message now takes 2,000 years, which is very nearly the entire span of the Common Era, from the height of Rome to tonight. Cool the estimate further, to 100 civilizations, and the average separation passes 5,000 light-years, so a single back and forth requires more than 10,000 years. At that distance, the species that asked the original question may have changed beyond recognition or vanished entirely long before its own answer comes home. Sit with the structure of that result, because it is one of the strangest features of our situation. The more honest and modest our estimate of how many neighbors we have, the farther away the nearest of them becomes, and the longer any conversation stretches, until the very idea of a conversation dissolves. Optimism does not save us here. Even the dream of 1 million civilizations gives us a galaxy where hello and its reply outlast every government, every language, every institution that existed when the words were sent. The pleasant picture and the bleak picture lead to the same doorway. One of them just takes a little longer to get there. This is where the word closest begins, quietly, to betray us in a second way. When we hear closest civilization, the mind reaches for its only model, the closest town, a real place that exists right now, that shares our calendar and our weather, that we could drive to if we chose. But the closest civilization in a galaxy of this scale is nothing like the closest town. It is more like a message sealed in a bottle and thrown into an ocean so large that, by the time the bottle washes ashore, the language written on the note is no longer spoken by anyone alive. The physical distance is only the surface of the problem. Beneath it lies something far more corrosive, a slow dissolving of the very idea that distance can be beaten by patience, by effort, or by better machines. And notice what we have not yet added. We have not yet brought in the speed of light, which is about to make everything we have said feel optimistic. We have not yet brought in the problem of time, the fact that civilizations are not fixed points on a map, but brief events that flicker on and burn out. We have only counted the company in the friendliest way the numbers allow and discovered that even a crowded galaxy is a scattering of islands so far apart that no boat among them can reach another while its builders are still alive to remember why they set sail. The crowd, it turns out, does not cure the solitude. The crowd is the solitude, seen from a little farther back. Part 5. When light itself is too slow. Perhaps, you might think, this whole problem is just about travel. We cannot send ships across these gaps. Fine, but we do not need to. We do not have to visit anyone to make contact. We only have to send a signal, and a signal moves at the fastest speed the universe permits. Radio waves, laser pulses, any flicker of electromagnetic energy races across the void at about 300,000 kilometers per second. Surely, even if our ships are hopeless, our messages are not. Surely the speed of light is fast enough to bridge what our engines never could. It is a reasonable hope, and it is wrong, and the way it is wrong opens the second and harder layer of the whole problem. The speed of light is not merely very fast. It is the fastest that anything carrying information can ever be, by the deepest law we know. Nothing that carries a message, no particle, no wave, no signal of any kind, can move through space faster than light. This is not a limit of our technology that a cleverer civilization might someday overcome. It is woven into the structure of space-time itself. Einstein's special relativity, confirmed by more than a century of unforgiving experiment, establishes the speed of light as an absolute ceiling on the movement of information. No engine accelerates a photon. No breakthrough shortens the path, which means that light is not just the fastest messenger we have. It is the fastest messenger that any mind, anywhere, at any level of advancement, will ever have. Now apply that ceiling to the modest distances we were discussing. If two civilizations want to exchange a single sentence across 1,000 light years, the minimum possible time for that exchange is 2,000 years, not because their transmitters are weak, not because their engineering is crude, because the universe will not deliver the words any faster. The signal departs at the maximum speed reality allows, and it still takes a full millennium to arrive, and the reply takes another. 2,000 years is not a delay you wait out. 2,000 years is an extinction event for the meaning of the message. Consider what the world was 2,000 years ago, so the number stops being a number. The Roman Empire ruled the Mediterranean. The Han dynasty governed China. No nation now on any map had been founded. No language spoken today existed in its present form. No scientific framework, no religion in its current shape, no institution that orders modern life had yet been imagined. Suppose the Roman Senate had sent a message into the sky in a year near the dawn of the Common Era, and suppose a civilization 1,000 light years away had received it, understood it, and answered. That answer would be arriving at Earth right about now. The Senate has been dust for the better part of 2,000 years. The language the message was written in is no longer anyone's native tongue. The civilization that sent it does not exist in any recognizable form. The reply would be an answer to a question asked by ghosts, delivered to strangers who never heard the question and would not recognize the questioners as kin. Let yourself stand in that Senate for a moment. because the abstraction has a place and a smell. The marble is cool. Outside, the city is loud with carts and voices in a language that will not survive. Inside, a decision is made to send words to the stars, and there is a feeling in the room of reaching out, of saying, "We are here," to whoever might be listening. The message goes up and out, riding light, and the men who sent it go home to their suppers and their politics and their certain conviction that they are the center of the world. Now, let the room dissolve. 20 centuries pour past in a heartbeat, empires rising and falling like breath, and the answer those men hoped for finally crosses the last light year and arrives, faint and patient, at an earth they could not have pictured, addressed to no one, carrying the warmth of a hand that turned to dust before the reply was ever halfway home. No one on this end remembers asking. No one on that end is left to care. The signal worked perfectly. Everything else failed. Hold the weight of this, because it is the line the whole night turns around. If we send a greeting today, and the nearest neighbor is 1,000 light years off, the reply cannot reach us until roughly the year 4026. By the time it arrives, every single person alive on Earth tonight will have been dead for 2,000 years. Not most of us, not nearly all of us, every one of us. The civilization that sent the message may no longer exist. The civilization that receives the reply may not either. We are not describing a slow conversation. We are describing two monologues separated by an abyss so wide that neither speaker is alive to hear the other answer. This is worth pausing on, because we use the word conversation casually, and a conversation is a more demanding thing than it sounds. A conversation is not the mere transfer of data from one place to another. It is a reciprocal exchange, in which each party responds to the other's most recent words, and that requires shared context, both sides holding the same thread, the same understanding of what is being discussed and why it matters. On Earth, conversation works because it happens in real time, or close to it. You speak, I hear, I answer within seconds. Even a letter or an email works, because the delay is measured in hours or days, a span within which both of us still remember the question. A delay of 2,000 years does not slow a conversation. It annihilates the context that made it a conversation at all. By the time a response arrives, neither party remembers asking, and neither party would recognize the world the answer came from. The exchange carries no more living meaning than a clay tablet in a forgotten script dug from under a city no one remembers. You can study it, you can admire it, you cannot continue it because the conversation it belonged to ended centuries before you were born. Some will say, reasonably, that even a one-way detection would change everything. We would not need a reply. Simply knowing that another mind exists or once existed would reorder humanity's whole sense of itself, and that is true. A confirmed signal from another civilization would be the most important discovery our species has ever made, whether or not we could answer it. But notice what that hope quietly concedes. If the best we can realistically hope for is to detect a signal from a civilization that may already be gone, then we are not describing contact, we are describing archaeology. We would be studying the remains of someone else's existence, not sharing an experience with them. The word contact implies mutuality, something passing both ways, both parties touched and changed. Receiving an ancient signal from a civilization that fell silent before our species learned to write is not contact. It is eavesdropping on a ghost, leaning close to a voice that stopped speaking long ago and mistaking the recording for a hello. And this, remember, is the optimistic version, the one where the signal arrives at all. We have not yet asked how hard it is to be heard. Part 6. The impossible cost of being heard. When people imagine a civilization announcing itself to the galaxy, they tend to picture something like a lighthouse, a bright beam sweeping the dark, visible to anyone who happens to look its way. The image is comforting and intuitive, and the mathematics behind it turns a cosmic lighthouse into one of the most extravagant engineering projects the mind can conceive. Before we ask whether anyone is listening, we should ask what it costs to shout loudly enough to be heard, because the cost alone may explain a great deal of the silence. Think about what it would take to produce a radio signal still detectable after crossing 1,000 light-years. The power you need depends on several things at once: the frequency, the width of the signal, the sensitivity of the receiver on the far end, and, above all, whether you broadcast in every direction at once or focus your energy into a narrow beam aimed at a single target. Start with the generous option, broadcasting in all directions, which gives every star within range a chance to catch you regardless of where it sits. The trouble is that omnidirectional broadcasting is fantastically wasteful because the energy spreads across the surface of an ever-growing sphere. By the time that sphere has swelled to 1,000 light-years across, its surface is so enormous that the sliver of energy falling on any one star system has dwindled to almost nothing. To remain detectable by a receiver like our own best radio telescopes at that distance, an omnidirectional transmitter would have to radiate at power levels measured in tens of terawatts or more and sustain them without pause. To feel that figure, hold it against ourselves. The total power consumption of all human civilization, every city, every factory, every device on Earth, runs around 18 terawatts. A beacon, bright enough to be seen across even a modest stretch of the galaxy in every direction, would demand energy output many times humanity's entire budget, poured continuously into a single lamp for centuries or millennia. Maintaining a beacon like that begins to require harnessing a serious fraction of an entire star's output, an undertaking on a scale that dwarfs anything our species has ever attempted or seriously planned. Aiming the energy instead of spraying it changes the arithmetic dramatically, but it introduces a new and unforgiving cost. A tightly focused beam can concentrate power into a narrow cone pointed at one star, cutting the transmitter power required by factors of millions or even billions compared to broadcasting in every direction. Humanity has actually done this in a small way. The planetary radar at the Arecibo Observatory, one of the most powerful directed signals we ever produced, ran at roughly 1 million watts and could, in principle, have been detected across hundreds or even thousands of light-years by a receiver as sensitive as our own if it happened to be pointed back at us. But a directed beam lights up only a needle's width of sky. To survey the galaxy this way, a civilization would have to aim at each candidate star in turn, hold the beam there long enough to register, then rotate to the next and the next. With hundreds of billions of stars to address, even spending only seconds on each, the full survey would take longer than most civilizations are likely to last. You can shout in every direction and exhaust a star, or you can whisper precisely to one listener at a time and run out of years before you finish the list. This sets up a quiet paradox at the very center of the detection question. The civilizations most likely to be found are the ones spending the most energy to be heard. But spending energy on a beacon means taking it from everything else, from food, from infrastructure, from defense, from science. A civilization that pours a serious fraction of its energy into calling out to strangers who may not exist is making an extraordinary wager. It is betting that someone is listening, that they will catch the signal, that they will understand it, and that some return, whether knowledge or alliance or merely the comfort of being heard, will be worth the staggering price. For a short-lived civilization, that wager is close to irrational, and here we touch something almost tender about the whole enterprise. The return on a beacon, if it ever comes, arrives centuries or millennia after the investment is made. The generation that pays the cost will be long dead before any benefit could possibly reach home. Every interstellar beacon is therefore an act of intergenerational generosity so extreme that it shades into self-sacrifice, a gift sent into the dark by people who know, with certainty, that they will never live to see whether it was received, much less answered. To build and tend such a beacon, a civilization must care about minds it will never meet, on behalf of descendants who may have forgotten why the lamp was ever lit. When you frame it that way, the silence we observe starts to look less like absence and more like a decision. Perhaps the galaxy is not empty. Perhaps it is full of civilizations that ran exactly these numbers, weighed the cost of being a lighthouse against the vanishing odds of anyone seeing the light in time, and quietly chose to spend their energy on living instead of shouting. A civilization does not have to be dead to be silent. It only has to be sensible. And a galaxy full of sensible civilizations, each one having concluded that the beacon is not worth the price, would present us with precisely the quiet sky we find when we look up and listen. We can even put a kind of human face on the decision, because we are already living inside the early version of it. Every few years, someone proposes that humanity should build a deliberate beacon, a real attempt to announce ourselves to the galaxy, and every few years, the proposal runs into the same wall of objections. It would cost an immense amount. It would have to be sustained across generations who would see no return. It would commit our descendants, who cannot be consulted, to a project whose payoff, if any, lands thousands of years from now. And so we do not build it. We keep the money for things that help people who are alive. There is nothing cowardly or foolish in that choice. It is the obvious, humane choice, and it is almost certainly the same choice nearly every other civilization makes when it runs the same numbers. The galaxy may be silent not because no one can speak, but because speaking, honestly accounted for, almost never pays, and almost everyone, given the bill, decides to live instead. There is no malice in this, and that is part of what makes it land so heavily. No one is hiding from us. No one is refusing us. Each civilization is simply solving the same problem we are, looking at the same brutal economics, and arriving at the same reasonable answer that the cost of being heard across 1,000 light years is almost never worth paying when the audience may not exist, and the reply will arrive long after you are gone. The lighthouse is not switched off out of fear. It is never switched on because the math was always against it. And so the cost of shouting becomes one more layer in the wall. Not a wall of distance this time, but a wall of economics, each civilization standing at the edge of its own light, doing the sum and choosing, gently and rationally, to stay dark. Part 7. Our voice was never built to leave. Even setting the cost aside, even granting a civilization willing to pay any price to be heard, there is a law of physics that thins every signal toward nothing as it travels, and it works against us with quiet, mathematical savagery. The law is the inverse square law, and it governs how any signal spreading outward weakens with distance. When a transmitter sends a wave into space, that wave expands as a growing sphere, and the surface of that sphere grows with the square of the distance from the source. Double the distance, and the same energy is smeared across 4 times the area, so the signal becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. At 1,000 light years, the dilution involves squaring a number 16 digits long. The fading is not gradual and gentle. It is brutal, and it is built into the geometry of space itself. To feel what this does, look at our own broadcasts. Humanity has been leaking radio into space since the early 20th century, a slow exhalation of television, radar, and radio that has been spreading outward for roughly 100 years. This expanding shell of accidental noise, sometimes called our radiosphere, now reaches about 100 light years from Earth in every direction, and inside that bubble lie several thousand stars. 100 light years sounds like a meaningful reach, a real announcement, but here is the detail that hollows it out. None of those signals were ever built to cross space. They were built to reach antennas on the same planet, a few hundred miles away at most. By the time our television broadcasts have traveled even a few light years, they have thinned to levels far below anything a realistic receiver could pull out of the natural hiss of the cosmos. At 100 light years, our incidental leakage is no longer a signal. It is indistinguishable from the background warmth of the universe. Our accidental voice is, for all practical purposes, already silent past our own doorstep. Let yourself watch one of those signals leave, because the image is strangely beautiful even as it defeats us. A burst of energy lifts off an antenna and begins to spread, a thin shell of order racing outward at the speed of light. For the first fraction of a light year, it is still itself, still carrying its program, its words, its pattern. Then the shell grows, and the same fixed amount of energy must cover an ever larger surface, so the signal thins and pales and softens toward the temperature of empty space. By the time the shell has swelled to the size of our stellar neighborhood, the message has dissolved into the faint, even glow that fills all of space, the leftover warmth of the universe itself. The signal is not destroyed, exactly. It is diluted past recovery, spread so thin across so much space that no instrument could ever gather enough of it back together to know it was ever a voice. That is the fate of nearly everything we have ever broadcast. What about signals we send on purpose, with real power behind them? In 2025, a research team led by Sophia Sheikh at the SETI Institute published a careful study titled Earth Detecting Earth, which modelled how detectable our own technological signatures would be from the viewpoint of an alien observer. The result is sobering in both directions. Earth's most powerful deliberate transmissions, the planetary radar pulses from the now-retired Arecibo Observatory, could in principle be detected from distances as great as 12,000 light-years, but only by a receiver as sensitive as our very best instruments, pointed in exactly the right direction, tuned to exactly the right frequency, at exactly the right moment. Our passive, everyday emissions, the broadcast television and cellular chatter that supposedly announces us to the stars, fade into noise within a single light year. Even our loudest intentional shout into the cosmos is a whisper measured against the silence it has to cross, and our ordinary daily noise does not survive the trip to the nearest star at all. This builds an asymmetry that quietly undermines the whole logic of passive listening, the logic on which most of our search for alien life has rested. When we scan the sky for signals, we are implicitly assuming that at least some civilizations are building powerful transmitters and aiming energy our way, on purpose or by accident. But we have just seen what the energy requirements actually are. A signal readable at 1,000 light-years demands either enormous power focused into a narrow beam aimed precisely at the target, or a broadcast in all directions that approaches the output of a star. Broadcasting everywhere is almost impossibly expensive. Beaming precisely is more feasible, but it requires knowing exactly where to aim, which requires already knowing where the target civilization is. And you cannot know where to aim if they have not announced themselves, and they cannot announce themselves without facing the same impossible choice. The would-be speakers are all waiting to learn where to point, and none of them can find out without someone else speaking first. This is not a small technical snag. It is a structural feature of interstellar communication, and it grows worse with distance. The farther apart two civilizations are, the more precisely each must aim, the more energy each must spend, and the less likely they are to stumble into mutual detection by luck. Distance does not merely add a delay to the conversation, the way we saw with the speed of light. Distance also drains the signal of its strength and tightens the aim required to deliver it, so that the very act of being heard gets harder along every axis at once as the gap grows. It is worth dwelling on how strange this asymmetry really is, because it overturns an assumption we almost never examine. We tend to imagine that a sufficiently advanced civilization would naturally be loud, that technology and visibility rise together, that a species clever enough to cross the stars would blaze across the sky as a matter of course. The inverse square law says otherwise. Visibility does not come free with intelligence. Visibility has to be purchased continuously at enormous cost against a law of physics that is always working to erase you. A civilization 1,000 times more advanced than ours is not automatically 1,000 times easier to see. If it has learned to use its energy efficiently, it may be far harder to see than we are, precisely because it wastes so little of itself into the dark. The night sky is not quiet because the clever ones have not arrived yet. It may be quiet because the clever ones learned, long ago, not to shout into a medium that swallows every shout. So we now have two great barriers stacked on top of each other, and they compound. The first is time, the merciless 2,000-year round trip that outlives the speakers. The second is faintness, the inverse square law thinning every honest signal toward the temperature of empty space, so that even a message sent in the same era as our listening might arrive too weak to separate from the natural noise of the sky. A civilization could be out there right now, this very moment, broadcasting with real intent, and we could fail to hear it, not because it is silent and not because it is gone, but simply because 1,000 light-years of space has rung its voice down below the threshold where any of our instruments can tell it apart from the hum of the universe. And we have still not reached the hardest part, which is not whether the signal arrives strong enough, but whether anyone is tuned to the right channel, in the right direction, in the right brief window of years, to catch it when it does. Part 8. The Gauntlet of Alignment. Suppose we grant everything we have so far refused to grant. Suppose a signal is sent with enough power to survive the crossing, by a civilization willing to bear the cost, aimed somewhere in our direction. There remains a gauntlet of alignments that must all be passed at once, and each one is its own narrow gate. The first gate is frequency. Electromagnetic radiation spans an enormous range, from radio waves measured in meters down to gamma rays smaller than the nucleus of an atom. A civilization that chooses to broadcast must pick a frequency or a band of frequencies out of that whole spectrum. A civilization that chooses to listen must also pick which frequencies to monitor. If the two choices do not overlap, neither will ever hear the other, no matter how close they are, how powerful the signal, or how badly both sides want to connect. Our researchers have traditionally focused their listening near the hydrogen line at 1420 MHz, on the reasoning that hydrogen is the most common element in the universe, and that any scientifically minded species would recognize its natural signature as an obvious meeting place. This is a thoughtful guess. It is also a deeply human one. An alien civilization with a different scientific history, a different atmosphere shaping which frequencies pass through its skies, or a different set of instincts about what counts as obvious, might choose an entirely different channel. They might prefer lasers to radio. They might use methods we have not even conceived. Every frequency we choose to monitor is a bet, and every bet we place on one channel is a bet we are not placing on millions of others. We are guessing which door our neighbour will knock on, out of a corridor of countless doors, and we have time and instruments to watch only a handful at once. This worry has driven a parallel search known as optical SETI, the hunt for civilizations signalling with laser light instead of radio. The logic is appealing because lasers are far more efficient than radio for point-to-point communication across these distances. A powerful enough laser pulse, even one lasting only billionths of a second, can briefly outshine its own star, making it detectable across hundreds or thousands of light years by a telescope built to catch such flashes. Dedicated programs have searched for exactly this, among them the Harvard All-Sky Optical Survey and the panoramic SETI experiment at Lick Observatory, which watches wide stretches of sky for sudden, anomalous pulses of light. But optical searching faces its own version of the alignment problem, and in some ways a crueler one. A laser beam is extraordinarily narrow. A beam built for interstellar communication, even after spreading across hundreds of light years, might illuminate a region only a few times the width of a planet's orbit at the receiving end. That tightness is precisely what makes the laser efficient, because all the energy goes one way instead of bleeding across the sky. But it also means the beam must be aimed with almost unimaginable precision at the target system. A misalignment of a fraction of an arcsecond, a hair's twitch across cosmic distance, sends the beam past us entirely, into empty space. The very thing that solves the energy problem makes the targeting problem worse, and there is no arrangement that solves both at once. Then comes the gate of time, which is the quietest and most merciless of them all. Even if two civilizations choose the same frequency, they must also be transmitting and listening during overlapping windows. A civilization that broadcasts for 10,000 years and then falls silent is detectable only during that 10,000-year window. A civilization that begins listening after the broadcaster has gone quiet finds nothing. And the universe does not store signals for later. Radio waves do not pause and wait for someone to tune in. They sweep through a region of space at the speed of light and continue onward forever. If no receiver sits in the right place, at the right time, tuned to the right channel, the signal is simply lost. It does not linger. It does not accumulate. It passes, and it is gone. We have tested ourselves against this gauntlet with patience and rigor, and the results are quietly instructive. The SETI at Home project, which ran from 1999 and published its final analysis in August of 2025, was, for 2 decades, the largest distributed computing effort in history. It enlisted millions of volunteers around the world to lend the idle moments of their personal computers to sift through radio telescope data gathered at the Arecibo Observatory. The data covered 14 years of observation across nearly the entire sky the telescope could see, and it contained billions of candidate detections, brief excesses of power, pulses, patterns that warranted a closer look. Each candidate was processed, classified, and ranked by how likely it was to be artificial. The scale of the effort deserves a moment of respect. Billions of individual detections sifted, millions of computers contributing. It was the most exhaustive search ever conducted through a single astronomical dataset for evidence of another civilization. The final results, published by David Anderson, Eric Corpella, and their collaborators, identified many signal candidates, clusters of detections that could plausibly trace to a single source in the sky. Every one of those candidates was then put through rigorous filtering to remove signals from known interference, satellites, aircraft, and the instruments themselves. The conclusion was unambiguous. Not one credible extraterrestrial signal survived. Every candidate that made it past the first screening was, in the end, explained by something terrestrial or instrumental. 14 years of observation, nearly complete coverage of the visible sky, billions of detections, and 0 confirmed messages from anyone. This did not surprise the people who do this work, and the reason it did not is the whole point. Researchers had long understood that the odds of detection in any single survey are low, given how enormous the search space is across frequency, across time, across position in the sky. But the SETI at Home result gave that abstract understanding a concrete weight. This was not a quick glance at a few hundred stars. It was a 14-year census of the radio sky, and it returned silence. That silence is not proof of an empty galaxy. It is something more precise and more useful. It tells us that within the volume Arecibo could reach, across the frequencies it watched, during the years it listened, no one was broadcasting a signal both powerful enough and aimed well enough for our instruments to catch. Each of those qualifiers matters. The null result rules out one slice of the possibilities. It says nothing about civilizations broadcasting on channels we did not watch, at powers below our threshold, or in directions that never included our small corner of space. The deeper lesson is that detection is not a single obstacle to be overcome with a better telescope. It is a system of interlocking conditions that must all be satisfied together. The broadcaster must be transmitting during the listener's lifetime. The signal must still be above the noise after the crossing. The frequency must match what the listener is watching. The beam, if it is aimed, must fall close enough to illuminate the listener's star, and the listener must have instruments sensitive enough to tell the signal apart from the natural sources and the terrestrial clutter. Fail any one of these, and there is no detection. And these conditions are not independent of one another. They compound. The probability of succeeding on all of them at once is the product of each separate probability, and when you multiply a handful of small chances together, the result collapses towards zero with a speed that should take your breath. This is why decades of ever better instruments have found nothing. The problem was never the sharpness of our tools. The problem is the number of needles that must thread the same eye in the same instant. Part 9. The problem of sharing a moment. Everything we have discussed so far has treated distance as the enemy, but there is a second dimension to this problem that is just as fatal and far less often examined. When we picture the nearest civilization, we imagine it as a fixed point on a map, something sitting still, waiting to be found, like a city on a globe. But civilizations are not fixed points. They are temporary events. They flicker into being, burn for a while, and go out. So the real question is not only how far away the nearest civilization is in space. The question is also how far away it is in time, and those two distances multiply each other in a way that destroys the last comfort the word nearest still offered. Begin with the stage on which all of this plays out. The Milky Way is about 13.6 billion years old, but for most of that history, it was not a place where a technological civilization could exist. The first several billion years were ruled by an early generation of massive stars that burned hot and died young, and those stars contained almost none of the elements heavier than helium because those elements had not yet been forged anywhere. Carbon, oxygen, nitrogen, silicon, iron, the very ingredients that rocky planets and complex chemistry require, simply did not exist in any abundance. They had to be cooked in the cores of generations of stars and scattered across space by supernova explosions before the universe held enough of them to build worlds like ours. Conservative estimates suggest that conditions suitable for habitable rocky planets did not become common until roughly 8 to 10 billion years ago. That gives us a window of about 8 to 10 billion years, during which technological life could even theoretically have arisen. That window is the stage. Now look at the actors. Human civilization has been able to produce detectable electromagnetic emissions for about 100 years. Radio began in the early 20th century, radar and television followed, and for roughly a single century, Earth has been announcing its technological presence through energy leaking into space. 100 years, set against a window of 8 to 10 billion. To feel that ratio, shrink the entire history of the habitable galaxy down into one calendar year. January 1st is the moment conditions first allowed technological life. December 31st, the final midnight, is tonight. On that calendar, Earth's entire technological lifetime, everything we have ever broadcast, occupies the last third of the final second of the year, not the final minute, not the final 10 seconds. Roughly 316 milliseconds, a span shorter than a single human pulse. Everything humanity has ever sent toward the stars fits inside a flicker too brief to notice. This is the overlap problem, and it is the quiet center of the whole night. For two technological civilizations to find each other, they must not only exist in the same galaxy, at distances that could ever be bridged. They must also exist at the same time, and not merely overlap in some loose biological sense. They must overlap in their technologically detectable phase, both of them actively sending or listening during the same window. If one civilization broadcasts for 10,000 years and then collapses, and a second arises 5 million years later, they will never know about each other. The galaxy will have hosted them both. They might even have occupied neighboring star systems. And their mutual ignorance would be total, a separation not of space, but of time, absolute and unbridgeable. The arithmetic of this is merciless. Suppose civilizations arise at random across the galaxy's habitable history, each lasting, say, 10,000 years in its technologically active phase. 10,000 years is generous by the standards of human history, but it is a blink against cosmic time, just one part in a million of the available window. For two such civilizations to overlap, their two separate millionths of the timeline have to coincide. Imagine the difficulty of that, lighting 10,000 matches at random moments across a span of billions of years and hoping that any two of them burn at the same instant. Most flames rise and fall alone, having never shared the dark with another. The galaxy could host thousands of civilizations across its history, and still, at any given moment, hold only a handful that are simultaneously alive and listening, scattered so widely that the gaps between them swallow any hope of contact. This is the realization that a careful study published in 2026 by the researchers Rava and Rahani in the monthly notices of the Royal Astronomical Society made quantitative. They modelled the expected number of coexisting civilizations as a function of how long civilizations last and how often a habitable planet produces technological intelligence. Their central finding was stark and clarifying. Civilizational lifetimes in the range of 5,000 to 100,000 years are, in their words, fully consistent with the Fermi paradox, the long-standing puzzle of why a galaxy that should be full of life appears so silent. Multiple civilizations may exist, one after another, or even overlap in time, and still fail to detect one another, simply because they do not last long enough for communication or travel to bridge the gaps between them. The galaxy does not need to be empty to appear empty. It only needs to be populated by civilizations that do not endure long enough to find each other. The silence we hear is not necessarily the silence of absence. It may be the silence of brevity. Let that settle, because it changes the shape of the loneliness. We are used to one kind of cosmic dread, the dread of emptiness, the fear that the universe is large and we are small, and perhaps no one else is here. That is a familiar ache, and many people have made their peace with it. But this is a different and stranger dread. It is the possibility that the galaxy could be alive and still feel perfectly, irrevocably empty, full of minds, dense with company, humming with civilizations asking the same questions we ask, and not one of them able to know that any of the others were ever there. The emptiness in that picture is not a fact about the universe. It is a fact about the gaps, in space and in time, between the things that fill it. Consider what it would mean for the galaxy to contain, right now, 10,000 civilizations, the figure that gives an average separation of around 1,000 light-years. 10,000 sounds abundant. It sounds like a crowded sky, but spread 10,000 points through a disk 100,000 light-years across, and each one ends up sitting near the center of a sphere of silence, roughly 2,000 light-years wide, within which no other living civilization currently exists. At the center of that sphere, a civilization broadcasts, listens, searches, and wonders. It does everything correctly. It builds the most powerful transmitters it can engineer. It scans the sky with patience and care, much as our own Breakthrough Listen program now sweeps thousands of stars across billions of channels, year after year, and it finds nothing. Not because the galaxy is empty, but because its nearest neighbor is 1,000 light-years away, A round-trip message takes 2,000 years, and neither civilization lasts long enough to complete the exchange. Each one is surrounded by others. Each one is, in every way that experience can measure, alone. That is the cruelty hidden inside the overlap problem. It does not merely make contact unlikely, it guarantees that the experience of every civilization, no matter how crowded the galaxy actually is, will be the experience of solitude. Proximity exists on the map. It does not exist in the living of it. We could be one of 10,000 voices, and still each voice, including ours, would look up into the same quiet sky and conclude, with the best evidence it could gather, that it was the only one ever to speak. And we have not yet asked the question that decides everything, the question the Drake equation leaves for last and we understand least. We have not yet asked how long anything we build can actually last. Part 10. How long anything we build can last. The single most important number in the entire search for other minds is also the one we understand least. It is the final term in the Drake equation, the average lifespan of a communicating civilization, usually written simply as L. Every other factor in the equation describes how often civilizations begin. This last one describes how long they endure once they have begun, and it is decisive, because a civilization that lasts only a few centuries can barely be detectable at all across these distances, while one that lasts 1,000,000 years would change the whole picture. We have exactly one data point for L, ourselves, and we do not yet know our own value because we are still in the middle of our story. But we are not entirely without evidence, because our own planet has run this experiment many times, and the record it has left is not encouraging. Every complex civilization that has ever arisen on Earth has eventually collapsed, fragmented, or been absorbed by a successor. The pattern is so consistent that historians and archaeologists treat the decline of complex societies not as an anomaly to be explained away, but as a structural feature of complexity itself. Consider the record. The Akkadian Empire, often called the first true empire in human history, unified Mesopotamia under a single centralized government around the year 2300 before the Common Era. It was powerful, literate, and administratively sophisticated. It collapsed within roughly 2 centuries, undone most likely by a combination of prolonged drought, internal rebellion, and pressure from surrounding peoples. 200 years from rise to ruin. The Neo-Assyrian Empire, one of the most militarily dominant states the ancient world produced, controlled territory stretching from Egypt to Iran at its height. It held its imperial form for around 3 centuries, before collapsing with startling speed between the years 612 and 609, before the Common Era, when Babylon and its allies dismantled in a handful of years a structure that had taken centuries to build. Classical Rome, counting both its republican and imperial phases, from the traditional founding of the Republic in the year 509 before the Common Era to the fall of the Western Empire in the year 476, lasted about 1,000 years, which is genuinely exceptional. But Rome's technological civilization, the phase in which it possessed advanced engineering, widespread literacy, long-distance trade, and centralized infrastructure, occupied a narrower window than that 1,000 years suggests. The aqueducts, the roads, the architectural mastery of the imperial age degraded badly across Western Europe within a few centuries of the empire's fall. Those capabilities were not quietly preserved in the background. They were lost and had to be rediscovered or reinvented many centuries later. The classic Maya civilization, which built sophisticated mathematics, astronomy, writing, and monumental cities across the Yucatan, went through a dramatic collapse between roughly the years 800 and 1000 of the Common Era. Cities were abandoned, populations fell, and although the causes are still debated, with drought, warfare, deforestation, and political fragmentation all among the suspects, the pattern is wearily familiar. A complex society that had sustained itself for centuries reached a threshold it could not survive and came apart within a few generations. The Ottoman Empire endured for about 6 centuries, from the late 13th century to the early 20th, an impressive span, yet the empire transformed so completely across those centuries that its early society would be barely recognizable to its final citizens, and when the end came, it came within the span of a single human lifetime, driven by defeat, revolution, and the redrawing of maps by outside powers. What these examples share is not a single cause of death. It is a common vulnerability. Complex civilizations are held together by intricate networks of resource distribution, social cooperation, and institutional memory. Those networks are robust within a certain range of stress and dangerously fragile beyond it. Drought, plague, invasion, the exhaustion of a key resource, internal corruption, a disruptive new technology, any of these can push a complex system past the limit of what it can absorb. And once decline begins, the very interconnection that made the civilization powerful begins to accelerate its unraveling. Supply chains break. Specialized knowledge, held in too few hands, is lost. Populations scatter. Within a few generations, a civilization that felt permanent to everyone inside it reveals that it was temporary all along, and the people living through the fall almost never see it clearly until it is well underway. If this pattern applies to technological civilizations in general, and there is no reason yet to think it does not, then the L in the Drake equation is not a number we may set wherever we please. It is constrained by a fragility that seems built into complex, interconnected societies. A civilization that lasts 10,000 years would already be an extraordinary outlier by the standards of our planet's record. One that lasts 100,000 years would be unprecedented by a factor of 100. The casual assumption that alien civilizations routinely persist for millions of years is not merely optimistic. It quietly requires that alien societies have solved a problem no human civilization has ever solved, the problem of permanent stability in a complex system, and they would have to have solved it while standing on planets that supply a steady stream of external shocks, volcanic eruptions, asteroid impacts, climate swings, the slow changes of their own stars, each one testing that stability on every timescale. There is a tempting rebuttal, and it deserves a fair hearing, because it seems at first to break the whole argument. Perhaps some civilizations do last far longer. Perhaps a few endure for millions of years, building technologies so advanced that they can simply bridge any gap, settle the galaxy, and wait out the centuries with patience we cannot imagine. If even a small fraction of civilizations achieve that kind of longevity, they would come to dominate the galactic stage. A civilization lasting 100 million years would overlap with thousands of shorter-lived neighbors. It would have time to send signals to every star in the galaxy and to wait for replies from thousands of them. But notice what this does to the puzzle. It does not ease the silence. It sharpens it, because the absence of any such civilization becomes far harder to explain. If long-lived, galaxy-spanning civilizations exist, where are they? Their monuments, their beacons, their reshaped stars should be obvious, and we see none of it. So the very fact that we observe no trace of such civilizations, despite decades of looking, points us toward a small set of uncomfortable possibilities. Perhaps long-lived civilizations are vanishingly rare. Perhaps they exist but have chosen to stay quiet or are undetectable by the methods we have. Perhaps they are out there and we simply have not yet looked in the right place at the right moment. Or perhaps the very idea of a million-year civilization is something close to a contradiction, because the same processes that produce technological intelligence also produce the conditions for its eventual collapse. Each of these possibilities fits the silence we observe, and not one of them offers any comfort to a species hoping to find a neighbor within reach. The likeliest reading of our own history is that civilizations are brief, that L is small, and that brevity, more than distance, is what keeps the lights from ever shining at the same time. The galaxy may not be a city. It may be a long, dark night crossed by separate, short-lived sparks, almost none of them burning together, almost none of them close enough to see another, while their own flame still holds. Part 11. Blind even at the doorstep. It would be reasonable to hope that all of this dissolves with better instruments, that the silence is just a measure of our youth, and that the gap is closing every year. There is a narrow sense in which that is true, and a much larger sense in which it is not, and the difference between them is best seen by looking at the single most studied nearby planetary system we have. To understand how far we are from detecting life around a distant star, watch how hard it is to learn anything at all about worlds practically on our doorstep. The TRAPPIST-1 system sits about 40 light-years away, which by every standard we have used tonight is essentially next door. At its center is an ultra-cool red dwarf orbited by 7 roughly Earth-sized planets, 3 of which fall within the band where liquid water could in principle exist. Since its launch, the James Webb Space Telescope has made this system a primary target, precisely because it is the best nearby laboratory we have for studying potentially habitable worlds. If there were ever a case where nearness and attention should hand us a clear answer about a planet's capacity for life, this is it, 40 light-years away, 7 planets to examine, the most powerful space telescope ever built, designed for exactly this kind of work. And the results show, with humbling clarity, just how hard this remains, even at the easiest possible range. In 2025, a team led by Anna Glidden at the Massachusetts Institute of Technology used the James Webb Telescope to gather transmission spectra of TRAPPIST-1e, the planet best placed within the habitable zone. The data were contaminated by features from the surface of the host star itself, a known difficulty when observing planets around active red dwarfs, because the star's own blemishes can masquerade as signals from the planet's air. After accounting for that contamination, the team found that the data did not lean strongly for or against the planet having an atmosphere at all. Hydrogen-dominated atmospheres were ruled out. Compositions like those of Venus or Mars were disfavored. But atmospheres dominated by nitrogen, with traces of methane and carbon dioxide, remained entirely possible. The result was not a detection, it was not a clean non-detection. It was irreducible ambiguity, the best telescope our species has ever built, unable to say for certain whether a planet 40 light-years away holds an atmosphere or not. Then, in April of 2026, a study published in Nature Astronomy by Gillen and collaborators delivered news more sobering still. Using the James Webb Telescope to measure the thermal emission of the 2 innermost TRAPPIST-1 planets, the researchers found that both worlds radiate heat in a way consistent with bare rocky surfaces, lacking any thick atmosphere. Models with substantial surface pressure were strongly disfavored for both. The 2 planets closest to the star appear to be stripped, airless rock baking under their sun. This does not rule out atmospheres on the more distant, more temperate worlds further out in the system. But it demonstrates that even in a system practically built for our telescopes, even in our nearest well-studied planetary laboratory, the question of whether any of these worlds could host life remains painfully unresolved. Now carry that difficulty outward and watch it become impossible. If the James Webb Telescope struggles to characterize atmospheres at 40 light-years, what hope is there of detecting the signs of life, let alone the signs of technology, at 500 or 1,000 or 5,000 light-years? The honest answer, with the instruments we have or can foresee for decades, is effectively none. Reading a planet's atmosphere requires catching it as it crosses in front of its star, and measuring the sliver of starlight that filters through its air, a signal often measured in parts per million of the star's total brightness. Push that to greater distances, and the star grows dimmer, the transit signal smaller, the noise larger. Beyond a few hundred light years, individual planetary atmospheres become unreadable by any instrument that exists or is seriously planned for the coming decades. The proposed Habitable Worlds Observatory, a future flagship designed specifically to image and study Earth-like planets directly, is not expected to fly until the 2040s at the earliest, and even when it does, its reach will extend only to stars within a few tens of light years, a tiny bubble holding a few thousand systems. This is the hard flaw under all our hopes. Our ability to learn whether a nearby world holds life, let alone a civilization, is confined to our immediate stellar neighborhood, and that neighborhood, in galactic terms, is microscopic. The volume within 100 light-years of Earth contains roughly 14,000 stars. That sounds like a generous number until you set it against the galaxy's 400 billion. 14,000 is about 1 in 30 million of the Milky Way's stellar population. If the nearest civilization is 1,000 light-years away, it lies far outside the small sphere we can study in any detail. We could not read its atmosphere. We could not find the chemistry of its life in the light of its planet. We could not photograph its surface. The only way we could know it existed at all is if it were actively broadcasting powerful signals straight at us, and we have already watched, through every barrier of this night, how unlikely that alignment is. There is a way of naming the time dimension of this problem that makes it especially clear, an idea explored by the physicist Claudio Grimaldi and others, sometimes called the contact era. The reasoning is simple. A civilization begins emitting detectable energy at some point in its history, and those emissions expand outward at the speed of light, forming a growing shell, the radiosphere. Earth's radiosphere is currently about 100 light-years in radius, a bubble of our noise centered on the sun, swelling at light speed in every direction. Any civilization inside that bubble, with sensitive enough instruments, could, in principle, detect us. But 100 light-years is tiny, and the galaxy is 100,000 light-years across, so our announcement has reached less than 1/10 of 1% of the galaxy's span. The overwhelming majority of stars, including any that might hold a civilization, lie far beyond the edge of everything we have ever broadcast. The contact era is the span of time after a civilization starts broadcasting, during which the odds of someone else detecting it become meaningful. Grimaldi's analysis showed that unless civilizations are extraordinarily abundant, that era lasts only hundreds to thousands of years, and for a galaxy holding perhaps 10,000 civilizations at once, the contact era for any single one is something like 300 to 1,000 years. This means that for the first several centuries of its electromagnetic life, a civilization is effectively invisible to the rest of the galaxy, because its signals have not yet traveled far enough to reach any likely listener. Earth is about 100 years into its electromagnetic life. If the contact era is several centuries, then we have not yet existed long enough as a broadcasting world for our presence to be statistically likely to have reached anyone at all. We are shouting into a room, and our voice has not yet had time to reach the walls. The room may be full, it does not matter yet, because the sound of us has not arrived and may fade before it does. And there is a further turn to this because we have been assuming that civilizations, once loud, stay loud. They do not. Part 12. The slow turning towards silence. There is a phenomenon hiding inside our own recent history that quietly shortens every window we have been describing, and it operates independently of how long a civilization lives. It is the tendency of an advancing civilization to grow quieter, not louder, as it matures. We assume that a technological species, once it learns to broadcast, keeps broadcasting, getting louder as it gets more capable. The opposite appears to be true, and we can watch it happen on our own planet across a single human lifetime. In the 1950s and 60s, Earth's leakage into space was dominated by powerful analog television transmitters, broadcasting megawatts of power from tall towers in every direction. These signals were genuinely omnidirectional, and though they were weak by interstellar standards, they were the loudest unintentional emissions our planet has ever produced. Then the trend reversed. By the 1990s, cable television had begun replacing over-the-air broadcast. By the 2000s, streaming delivered over fiber optic cable was displacing both. Cellular networks, though they are everywhere, use low-power transmitters designed to reach a tower a few miles away, not a receiver among the stars. Each generation of our communication technology has become more efficient, more targeted, and quieter. The pattern is unmistakable. Humanity is becoming electromagnetically dimmer with every passing decade, not because we communicate less, but because we communicate better. Efficiency means sending energy exactly where it is needed, instead of spraying it across the sky. And energy sent precisely is energy that no longer leaks into space for anyone to overhear. If this trajectory continues, Earth's accidental signature may peak within a century or two of the dawn of radio and then fade back toward undetectability. A civilization watching our solar system from 100 light-years away might have noticed a faint rise in radio noise from our direction beginning in the 1920s. By the year 2100, that noise may already be thinning. By 2200, it may be gone entirely, replaced by a communication system so efficient that nothing escapes into space at all. From the outside, Earth would appear to have fallen silent, not because our civilization ended, but because it grew up. We would have passed through our loud phase and out the other side, into a quiet maturity that, to any distant listener, would look exactly like death or absence. Project that onto a whole galaxy of civilizations, and the consequences are severe. If the electromagnetically loud phase lasts only 1 to 3 centuries out of a civilizational lifespan of 10,000 years, then at any given moment, only 1 to 3% of all existing civilizations are detectable through their leakage. The overlap window we worried about earlier now shrinks again. 2 civilizations must not only overlap in their total existence, they must overlap specifically in their brief, loud phases. The probability of that double overlap is the product of 2 already small probabilities, and the result is a number so low that even a galaxy holding thousands of simultaneous civilizations might contain not a single pair that is mutually detectable at any given moment. The galaxy could be crowded with mature, quiet civilizations that passed through their loud phase long ago and now sit in electromagnetic silence, each one surrounded by neighbors in exactly the same condition. Everyone listening, no one broadcasting. The cosmos reduced to a waiting room where every civilization sits in silence, each one assuming the room is empty. This going dark effect adds something genuinely new to the wall we have been building, because it severs the link between how long a civilization lasts and how long it can be found. A civilization that endures for 100,000 years, but is loud for only 200 of them, presents the same detection profile as one that exists for only 200 years total. From the viewpoint of an outside observer scanning the sky, both are visible for the same brief flash, and invisible the rest of the time, present but unfindable, ghosts in plain sight. Longevity, which we hoped might rescue us, does not help if it is spent in silence. A patient, ancient, thriving civilization that has simply outgrown its noisy adolescence is, to our telescopes, indistinguishable from one that never existed. And there is a subtler layer still, one that operates even when 2 civilizations do coexist in time, do share a loud phase, and do choose compatible frequencies. They must also overlap in the pace at which they communicate, and there is no reason to assume they will. Human communication unfolds in seconds. Our transmissions pulse at frequencies of millions or billions of cycles per second, and we encode meaning in rapid modulations, fast flickers of change. When our researchers search for alien signals, they look for patterns that match this human tempo, narrowband tones that hold for seconds or minutes, pulses that repeat within an observing session. But there is no law that says an alien civilization must think or speak at our speed. The pace of cognition is set by biology, and biology varies. On Earth, nerve signals travel at speeds ranging from about 1 to 100 meters per second, and that sets the tempo of human thought, and, through it, the rhythm of human speech and human machines. A civilization evolved from organisms with a different inner architecture might think and communicate on a radically different clock. A slower biochemistry could produce minds that operate over hours or days rather than thousandths of a second, whose transmissions modulate so slowly that a single symbol takes weeks to complete. Observed by our instruments over a session of minutes or hours, such a signal would look like a featureless, constant tone, indistinguishable from the natural emissions of a star or a cloud of gas. It would be a message dense with meaning, passing through our receivers without tripping a single detection algorithm, because our algorithms are built to notice patterns that change at human speed. The reverse holds just as well. A civilization with faster cognition, perhaps built on electronics or light rather than slow biological nerves, might pack a whole message into billionths of a second, and our own broadcasts would seem to them like glacial, meaningless drifts in the background, too sluggish to register as anything intentional. Two civilizations could share the same galaxy, the same century, the same frequency, even aim at each other, and still fail to recognize one another's signals because the very tempo of their thought is mismatched by orders of magnitude. The universe may separate minds not only by distance and by time, but by the speed at which they think, ensuring that even overlapping broadcasting neighbors remain, to each other, nothing but noise. Part 13. A message we cannot read. Suppose now that against every probability we have stacked tonight, a signal arrives. Suppose a radio telescope picks up an unmistakably artificial, narrowband transmission from a star 1,000 light-years away, confirmed by multiple observatories. Beyond any doubt, someone is out there. The most important moment in the history of our species has just occurred. And then a new problem begins, one that has nothing to do with distance, energy, or timing, and everything to do with meaning. The signal carries information, but information requires decoding, and decoding requires shared context, and there is no reason to assume we share any context at all with the mind that sent it. Let yourself sit in the room where it happens, because this is the moment we have all imagined, and it is not what we imagine. The screen shows a tone. It is clearly artificial, too clean, too narrow to be a star or a cloud of gas, holding steady where nothing natural holds steady. The room is very quiet. Someone says it again, almost a whisper. It is real, and no one moves, because everyone understands at once that they are looking at proof that we are not alone, and that they have no idea what they are looking at. The tone shifts, slowly, in ways that are obviously deliberate and completely opaque. There is structure in it, the unmistakable fingerprint of intention, and not one symbol of it can be read. Hours pass. The pattern continues, patient and unhurried, a voice modulating so slowly that a single one of its words may take days to finish, a sentence weeks, and the people watching realize that even as the meaning pours through their instruments, it is passing through them like water through open hands, recorded perfectly and understood not at all. They are in the presence of a message and locked out of it, holding the envelope, unable to open the letter, and the sender is 1,000 years away and may already be dust. This is the decoding barrier, and it is more formidable than it first appears. Human languages are mutually unintelligible without years of study, and every one of them evolved on the same planet, from the same kind of brain, shaped by the same senses and the same shared world. An alien signal would encode information structured by a mind that shares none of that with us, no common evolutionary history, no shared sensory experience, no overlapping references of any kind. People often propose that mathematics could serve as a universal language, that the sequence of prime numbers could act as a handshake, a way of proving intelligence across the void. That is probably true as far as it goes. A pattern of primes could indeed announce, "We are here, and we can count." But moving from "we know they are intelligent" to "we understand what they are telling us" is a chasm that no mathematical primer can reliably bridge. Proving you are a mind is not the same as making yourself understood. We have a humbling test case for this, right here on Earth. We have never once succeeded in fully decoding a communication system built by a mind fundamentally different from our own, and we do not have to look to the stars to find one. We struggle to decode the communication of dolphins, creatures that share our planet, our broad evolutionary lineage, our basic neural design, and a world of water and air we can at least partly imagine. We have studied them for decades, with affection and ingenuity, and we still cannot truly read them. The expectation that we would swiftly understand a message from a mind that evolved entirely separately, on a world we have never seen, shaped by senses we may not possess, is not optimism, it is fantasy. And it is a fantasy that assumes we even receive enough of the message to work with, because here is the final cruelty folded into the decoding problem. A transmission from 1,000 light-years away, thinned by the inverse square law, scattered by interstellar dust, competing with the natural radio glow of the galaxy and the clutter of our own machines, may arrive not as a clean stream but as a fragment, a few seconds of data, a partial pattern, enough to confirm, beyond doubt, that something artificial sent it, and not nearly enough to extract any real content. We would know that someone spoke. We would not know what they said, and we could not ask them to repeat it, because our request would take 1,000 years to arrive, and their answer, if they still existed to send one, would take another 1,000 to return. The conversation would be over before it began, ended by the same wall of time we have been climbing all night, now standing between us and even the meaning of a message we managed, against all odds, to catch. So consider what we have assembled, because the structure of it is the real subject of this entire night. The silence of the cosmos is not built from a single, overwhelming barrier that a heroic effort might someday break through. It is built from the accumulation of many separate obstacles, each one individually surmountable, that become collectively insurmountable when multiplied together. Distance weakens the signal. The inverse square law drains its energy toward the background warmth of space. Frequency misalignment hides it on a channel no one is watching. Temporal misalignment erases it because the universe does not store signals and no one is listening when it passes. Directional misalignment sends it through empty space beside us. The mismatch of mental tempo turns even a strong, well-aimed message into featureless noise. The decoding barrier locks away whatever meaning survives. And the speed of light, the fastest carrier of information that will ever exist, ensures that even when, by some miracle, all the rest of it aligns, the delay between question and answer outlasts the very civilizations attempting to speak. Each of these barriers, on its own, might be beaten by patience, by power, by a better telescope, by a cleverer code. That is what makes the situation so quietly devastating. We keep solving the individual problems, and the silence does not lift, because the problem was never any single one of them. The problem is that they all have to be solved at the same time, for the same signal, between the same two civilizations, in the same brief window when both happen to be alive and loud and aimed and listening. And the chance of all of those things coinciding in a galaxy this large and a history this long is so small that it can produce a perfect, total silence in a galaxy that is nonetheless full of minds. We are not necessarily alone. We may simply be unreachable and surrounded by others who are unreachable in exactly the same way. There remains only one more thing to do, which is to grant ourselves every wish at once, build the most generous scenario the universe could possibly allow, and see whether even that is enough. Part 14. The best case and the death of the word near. Let us build the kindest scenario the universe could possibly permit and grant every wish at once, because if the dream itself fails, the matter is settled. Suppose a technological civilization exists right now, this very moment, orbiting a star 1,000 light-years from Earth. Suppose it has endured for 50,000 years, making it extraordinarily long-lived by any reasonable estimate. Suppose it broadcasts powerful signals across a wide range of frequencies, with transmitters aimed in our general direction, pouring out energy that dwarfs anything humanity has ever produced, a beacon so bright that even our lesser instruments could catch it. Suppose, further, that this civilization is curious, that it wants to be found, that it has spent a serious fraction of its wealth on announcing itself to the dark. This is the dream. Every variable turned to its friendliest setting. Every barrier we have built tonight lowered as far as plausibility allows. And even here, even in this most forgiving of all possible universes, meaningful contact remains impossible. The signal from this civilization, traveling at the absolute speed limit of reality, takes 1,000 years to reach us. The light we see from their star tonight left it while Europe was in the middle of its Middle Ages. If they aimed a message at us 1,000 years ago, it is arriving now, carrying news of a civilization as it existed 10 centuries in their past. We cannot know what they are like today. We cannot know whether the power that authorized the message still governs them. We cannot know whether the language it was written in is still spoken, or whether the civilization itself survived the 1,000 years its message spent in flight. We receive a postcard from a past that may already be a ruin, with no way to check whether the sender still lives. And if we answer at once, our reply begins its own 1,000-year crossing, arriving in a year we will spell as 4,000 and beyond, 2 full millennia after their original message left home. The rise and fall of Rome would fit inside that pause. The invention of printing, the scientific revolution, the industrial age, the digital age, the whole of modern history, all of it could unfold in the gap between their question and our answer. This is not a conversation. It is 2 monologues separated by an abyss, each civilization speaking into the dark and waiting for a reply that, when it comes, addresses a version of themselves that no longer exists. And this, remember, is the best case. Strip away any single one of those generous gifts, and the picture collapses faster. Shorten their life to 10,000 years, the figure recent work suggests, and they may fall silent before our reply arrives. Lower their transmitter to something like our own, and their signal drowns in the noise before it reaches us. Remove the deliberate broadcasting, and they go quiet, visible only during a brief flush of leaky emissions that fades within a few light years. Remove the precise aim, and their beam passes through a patch of space we are not watching, on a channel we are not scanning, in a decade when our instruments point elsewhere. Each gift withdrawn does not merely lower the odds of contact. It erases them. The dream scenario is not a floor beneath which reality cannot fall. It is a ceiling reality will almost certainly never reach. This is what too far away finally means, in its fullest sense. When we say the closest alien civilization could be too far away, we do not mean only too far to visit. We mean too far for a signal to cross within the lifetimes of the civilizations on either end. Too far for mutual detection, given any realistic power and any realistic instrument. Too far for the overlap in time to be anything but a statistical miracle. Too far for shared meaning to survive the passage. Too far for the word contact to keep any of the weight we instinctively give it. Too far away is not a statement about miles or even about light years alone. It is a statement about the whole architecture of separation the cosmos imposes on any two minds that try to reach across it. Distance is one dimension of that architecture. Time is another. Detectability is a third. The brevity of any technological phase is a fourth. The alignment of speaking and listening is a fifth. Each one, on its own, threatens to make contact impossible. Together, they form a wall so complete that the question shifts from can we overcome it to whether there is anything left to overcome. Stand for a moment at the center of it, where every civilization in this picture is forced to stand. You are at the center of a sphere of silence roughly 2,000 light years across, and within it no other living civilization currently exists. You do everything right. You build the most powerful transmitters your species can engineer. You construct instruments of extraordinary sensitivity. You scan the sky with patience and rigor, year after year, generation after generation. And you find nothing, not because the galaxy is empty, but because your nearest neighbor is 1,000 light years away, and a round trip takes 2,000 years, and neither of you lasts long enough to finish the exchange. Now pull back and watch the cruelest detail of the whole scenario come into view. Your neighbor is doing exactly the same thing. They are at the center of their own sphere of silence, building their own instruments, scanning their own sky, finding their own nothing. If we are searching and finding silence, so are they. Whatever loneliness we feel, they feel in equal measure. Whatever hope we pour into the possibility of contact, they pour the same hope into the same futility. Each civilization is a mirror of every other, identical in its isolation, identical in its longing, identical in its inability to reach across the gap. They look at the same galaxy we do. They see the same stars. They ask the same questions, and they arrive at the same silence. The universe does not merely separate us. It ensures that each of us experiences the separation as total, and that no one, from the inside, can ever tell the difference between a galaxy that is empty and a galaxy that is full. That last point is the quiet center of everything. There is a cosmic veil drawn across our knowledge, and it cannot be lifted from the inside. No civilization knows whether the silence it hears is the silence of an empty galaxy or the silence of a crowded one, in which everyone is simply too far apart to be heard. The only way to learn which kind of galaxy you live in is to detect a neighbor, and the very distances and timescales that define the problem are precisely what prevent that detection. So you live and you die, and your whole civilization lives and dies, without ever knowing whether the cosmos around you was barren or teeming, whether your loneliness reflected the truth or only the limits of your reach. And this is why the galaxy could be alive and still feel perfectly, irrevocably empty, not as a fear, as a structure. A galaxy full of voices that spoke at different times, in different directions, at different frequencies, and for too brief a span to ever hear one another, would sound exactly as silent as a galaxy with no voices in it at all. There is one last possibility to face, and it deepens the word too far even further into time itself. What if the nearest civilization was close, genuinely close, a few hundred light years away, but it existed 10,000 years ago, or 100,000, or 1,000,000? Could we find its ruins? People have begun to search seriously for exactly this, for the traces a dead civilization might leave behind. A civilization that altered its planet's atmosphere might leave industrial compounds, chemicals like the chlorofluorocarbons we ourselves once produced, which have no natural source, or unusual levels of gases like nitrogen dioxide, a civilization that built enormous structures to capture its star's energy would leave a signature in that star's light, a dimming in visible wavelengths, and a glow of waste heat in the infrared. We have looked. A survey by Griffith and collaborators in 2015 examined roughly 100,000 galaxies for that infrared signature, and later work by Suazo and collaborators in 2022 and 2024 searched millions of individual stars, combining data from infrared and astrometric surveys. No confirmed signature of such a structure has ever been found. Either they are not being built, or they are built in ways our instruments cannot recognize, or they are so rare that our searches have not yet crossed the right star. But there is a gentler and more terrible reason the ruins may be missing. They may simply be too fragile to last. On Earth, the things we build decay on timescales of centuries to a few thousand years, not millions. Steel corrodes, concrete crumbles, plastics break down under starlight. Without constant maintenance, the physical body of a civilization erodes and is recycled by the slow chemistry of its own world. A planet that hosted a civilization 1 million years ago might show no trace of it at all today. Every structure, every road, every artifact erased by wind and water and the turning of the crust, the only evidence, a faint chemical anomaly buried in rock, readable only by standing on the surface and drilling down. From 1,000 light years away, such evidence is simply invisible. The cosmos does not preserve monuments, it dissolves them. Given enough time, every trace of every civilization is returned to the background, indistinguishable from the natural noise of the universe. So picture the most haunting version of all. The nearest civilization may have been close to us, a few hundred light years away, orbiting a star you could find on a clear night. It may have built cities, developed science, asked these same questions about its own silent sky. And it may have died 10,000 years ago, its atmosphere long since scrubbed clean, its structures long since worn to nothing, its broadcasts long since dispersed into the background hum of the galaxy. We look at its star tonight and see nothing unusual. We measure the light from its planets and find no anomaly. Every instrument we own reports the same verdict: an ordinary system, unremarkable, uninhabited. And the verdict is wrong. Someone was there. They were close. They were real. And we will never know, because the evidence of their existence has been reclaimed by the very same processes that will one day reclaim the evidence of ours. The message in the bottle has not merely washed ashore on a beach where the language is no longer spoken. The bottle itself has crumbled to sand, and the beach has been swept clean, and the ocean has forgotten it was ever thrown. The search will go on, and it should. Telescopes will scan new frequencies. Surveys will cover more stars. Instruments will grow more sensitive. And perhaps one day, against every probability we have weighed tonight, a signal will rise out of the noise, undeniably artificial, undeniably alien. If that day comes, it will be the most important moment in human history, and it will confirm that we are not the only minds the universe has made. And then the delay will begin, the long and terrible wait for a reply that may take centuries to cross from a sender who may no longer exist, carrying meaning that may no longer translate. Perhaps the real value of the search was never the handshake we imagined. Perhaps it was the honesty of looking, the refusal to call the sky empty until we had truly listened, and the discovery, slow and clean, of why the silence is so complete. To understand why we may never hear another voice would itself be a profound thing to know. It would tell us that the cosmos builds its minds in isolation and keeps them there, not out of any malice, but simply out of geometry, out of the plain arithmetic of distance and time and light. And so we end where we began, with a single word, now emptied of everything it once promised. Closest does not mean reachable. It does not mean detectable. It does not mean relevant. In a galaxy 100,000 light-years across, closest means only that among all the impossible separations, this one happens to be the least impossible, and the least impossible distance can still be a distance no signal, no ship, and no meaning will ever cross, while the civilizations on either end remain alive to care. The nearest alien mind may be out there tonight, orbiting a quiet star in an arm of the galaxy you can see from your window, building instruments to search for us, while we build instruments to search for them, both of them reaching toward each other, across a gap that light itself needs 1,000 years to cross. Both of them calling the other the closest. Both of them wrong about what that word has ever meant, and both of them, in the end, too far away to ever know the other was there at all.